Hopefully by now you've tried question number 3 and you've tried Gauss's problem, but just to kind of illustrate Gauss's problem in a relatively easy way, I'll just kind of quickly demonstrate what I personally picture. And while I'm no Gauss, I can probably infer that Gauss as a 7-year-old was basically as smart as me in my mid-30s and probably did this a lot faster than me anyway, but I assume this is kind of what he saw. When he saw the numbers from from 1 to 100 bending back on themselves, he probably pictured the numbers 1 to 50, and then from 51 to 100, kind of like that. I doubt that he actually pictured each individual number, because he already knew that each pair of numbers was already going to add up to the same thing, no matter where he pictured it. So whether he pictured the 1 and the 100 or pictured the end of the ribbon where the bend happens, the 50 and 51, he kind of saw the same thing. So I'm going to assume just for a moment that he was probably just thinking about the 1, the first term, and the 100, the last term, and picturing that. He knew that that added up to 101. And since he knew that the bend would happen at the halfway point where 50 switched to 51, then at that bend, he probably inferred, correctly so, then that forces 50 pairs of numbers to occur. So generally speaking, he was finding the sum of the first and the last terms, 1 plus 100, and then multiplying that by the number of pairs that represent each little matched set along the ribbon itself. So 101 times 50 ends up being 5,050, and that is the actual sum. If you wanted to take the time to add that up and actually wanted to do 1 plus 2 plus 3 plus 4 all the way to 100, you would end up with 5,050 yourself. But Gauss's strategy is so magnificent because of how practical it is. You really didn't have to know what all of those pairs were. You really just had to know two things: the sum of the first and the last terms. And for notation, I'm going to introduce something a little new that I'll mention in a second. The sum of what I'll call a sub 1 and a sub n, the first and the last terms. And the number of pairs that we had to add up. In this case, if you're adding all the integers from 1 to 100, you had 50 pairs of numbers that bent back on themselves in the ribbon. So this kind of strategy here, to take the sum of a sub 1 and a sub n times the number of pairs, actually kind of summarizes what we've done in all of the problems up to this point. If you go back and think about the example that we did in question number 1, regardless of which way you personally did it, you can see how this strategy could definitely work. The sum times the number of pairs refers in this case to the sum of the end numbers, first and last. 1 plus 10 is 11, times the number of pairs, 1, 2, 3, 4, 5 pairs of numbers, and that of course is 55. That also could have worked for question number 2, which we sort of demonstrated together. The sum of the first and the last was 1 plus 20, 21, times a total of 10 pairs. 21 times 10, 210. So this idea of sum times pairs is, in essence, the easiest and most efficient way to figure out the sum of a series. And that was Gauss's little trick. Without articulating it at the wee age of 7, that was basically what he was seeing when his teacher posed him that challenge to add up all the numbers from 1 to 100. He didn't see 100 discriminate terms. He saw a series of pairs. He found one sum and simply multiplied it by the number of pairs. Now, of course, there's something to be said for a 7-year-old who can multiply by a relatively big number in his head. But again, the point stands, he visualized the numbers differently than 1 plus 2 plus 3 plus 4, which could talk even a brilliant mathematician out of that task, because that just sounds so tedious. It sounds so time-consuming. And his strategy simply eliminated the need to do a long, tedious calculation. Now, Going forward, I do want to make sure that we think about this kind of formula that we've generated for ourselves, although I'm not going to formalize it quite yet. I've highlighted it here in this pink, the sum of the first and the last terms, and I'll just make sure that you're clear on my notation. A sub 1 is going to be my notation for the first term, and A sub n is going to be my notation for the last term. You'll see why in a second. But this little formula, sum of the first and the last times the number of pairs, can be adapted pretty easily to questions like question number 4. In question number, or actually, before I get to question number 4, let me just clarify question number 3. The sum of the integers from 1 to 50, if you've done this one already, hopefully you can see how this little formula will work for that. So I should actually do that before we do anything new. If you already have an answer for this, let's see if this validates it. The integers from 1 to 50 mean that the first term is 1 and the last term is 50. So remember how my formula is sum of first and last? I know I'm going to have to do 1 times 50. That's going to be the first part of my formula, times the number of pairs. From 1 to 50, that's going to be 25 pairs of numbers, figuring the bend is going to have to happen exactly halfway in between. So that's 25 pairs of numbers. 1 plus 50 is 51. 51 times 25, if you want to do that quick calculation, ends up being 1,275. So if you added that and found that answer in a different way, that's completely fine. But this is just proof Gauss's strategy totally works, no matter which way you do it. So the first plus last times number of pairs seems to be a pretty solid way of doing the problem. Now, let's adapt it to question number 4, and let's see if we can make some sense of that one. In question number 4, we can do the first plus last times number of pairs strategy. We just have to look carefully. This time, we're doing 2, 4, 6, 8, all integers, but in this problem, they're not necessarily the same series because it's counting by 2s. And in all the previous problems we've done so far, it was counting by 1s. So if you feel like it would be more secure right now when you're in uncharted territory to write out the numbers a little bit more paired up, like Gauss's ribbon strategy, you might want to take the time to do that. 2, 4, 6, 8, 10. Then we'd have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers in this series. So the bend is going to have to happen at 10, 12, 14, 16, 18, 20. It does kind of look like I can see Gauss's strategy paying off here, because notice the pairs that you've got. I like to highlight it just to see it, but notice my pairs. Sure enough, first plus last, 2 plus 20, is going to add up to the same thing as all the other pairs. All of these pairs are going to add up to 22. So I know that first plus last is going to be 22 times the number of pairs, 1, 2, 3, 4, 5. 5 pairs. 22 times 5 is 110. That must be the sum of my numbers. Now, if you're looking at that going, okay, this is easy, I got this. Here's one thing to keep in mind. Was it obvious that there were 5 pairs? Because I had to write it out for myself to see where the bend was going to happen. I had to visualize that little ribbon of numbers for me to go, oh, okay, 2, 4, 6, 8, 10, and now the numbers bend down. I wouldn't have necessarily thought that there were 5 pairs instinctively until I actually went and counted each of those individual numbers as its own independent term. And the reason I'm saying that is because if you need to think about this strategy in question number 5, it might be kind of hard to look at some of these and instinctively know how many pairs we have. Like, if you're looking at number 5, letter C, is it obvious how many pairs you're going to have? If you start at 15 and end at 205, I mean, we can definitely picture the ribbon starting at 15 and then at 25. And we could picture the ribbon ending at 205. 195 would have come before. I can definitely picture it. But the question is, how far down does the ribbon go? Like, how many pairs am I supposed to multiply by? How am I supposed to know what's kind of in the middle of that ribbon? So I'm hesitant right now to sort of jump into these problems in number 5 and say, okay, I got a strategy, I can do this. Because it feels like we have a bit of a a loose end. How do we know how many pairs? The formula that we're kind of generating for ourselves requires that we know the number of pairs. I don't feel confident I'm always going to know that number. And a formula is not very effective if I don't know what to plug into it. The first part of the formula seems okay. The first and the last, I can tell what those numbers are just by looking at problem letter C. First is 15, last is 205. Got it. That part's going to be easy. But number of pairs, I just don't know. So before we actually do some of these problems more independently, let's refine our formula a little bit. Let's see if we can put this formula in terms that we can be absolutely certain we'll know just by looking at problems like number 5, so that I don't have to do a whole bunch of tedious thinking. Because the whole point of this is to say, how can we be efficient? How can we channel our inner Gauss? Gauss wasn't going to write down all of the numbers from 15 to 205. He was standing in the corner doing this problem in a matter of seconds to impress his teacher. There's no way he was pulling out a pencil and paper. So why should we? If we can think like a 7-year-old Gauss, how can we think better? So let's go back for a moment, again, to some of the problems that we've already done, and let's see if we can think and strategize through customizing our formula. It might seem weird that here I am trying to show you how to customize a formula, and if you're sitting there thinking, Herbert, just tell me the formula. Just tell me how to do it. I want to implore you to really think about why I'm taking this strategy and why I'm deriving the formula with you step by step, instead of just telling you a formula that some random person made up that you can Google. You can definitely Google a formula, and I have no problem with you doing that. But I want you to see where the formula came from so that you can see how mathematicians think. Because most mathematicians don't just look up a formula and say, all right, here it is, let me use it. Most mathematicians, true mathematicians, come up with their own formulas. Even if it's something that they can Google, they still explore the mathematics themselves. So even though I know it might seem like it's inefficient, I am going to ask you to bear with me here as we develop a formula, rather than just Google a formula or look it up in a book, so that we can see what that mathematical experience is like. I think you'll find, hopefully, that it'll make sense why the formula that we end up with works, and then you won't have to feel like you're just randomly memorizing something. It'll have meaning because you'll know exactly where all the parts of the formula came from. So, just to recap, we are refining the current formula that we have. The current formula that we have is the sum of the first and the last times the number of pairs, and that formula is great if you know the number of pairs, terrible if you don't know how many pairs there are. That's what we're trying to improve. It's that number of pairs thing. So, let's think for a second about one of the more accessible examples. Question number 1, very accessible. It had 1, 2, 3, 4, 5 pairs. Now, I know that it had 5 pairs because I can see them. But, think about this. The numbers from 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 terms in that sequence. And half of them get paired up with the one above them. And I'm thinking about that number half because I'm thinking, well, that makes sense. If I have 10 of something, that's 5 pairs of them if I join them all together. Same thing in question number 2. If I have the integers from 1 to 20, that's 20 things. Pair them up, that's 10 things total. In number 3, the integers from 1 to 50, that's 50 things. And if I pair them all up, that's 25 pairs. So instinctively, if I think about this idea of pairs, I'm really thinking that a pair is just the total number of terms divided by 2, or half of the total number of terms. So if pairs are just however many numbers I have divided by 2, then my formula has kind of evolved a little bit. Now I'm thinking that my formula is the sum of that first and the last times the total number of terms divided by 2. Let's just check to make sure that would work for one of the problems that we've already done. Let's say question number 2. We already know that answer. So let's see if our new and improved formula would work. The sum refers to the sum of the first and the last. First is 1, last is 20. The total number of terms from 1 to 20 is 20 divided by 2. So 1 plus 20 is 21 times 20 divided by 2 is 10. 21 times 10, yep, that's 210. My new and improved formula works. So it looks like I've gotten a better formula. This is great. If I know the total number of terms, then I don't have to think about pairs. I'll just take the total divided by 2. That's easier. That, to me, seems more instinctive than the idea of pairs. Great, fantastic. So I could look at question number 4 and say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms. 10 divided by 2 is 5, times the sum of the first and the last. 2 plus 20 is 22. 22 times 5, yep, that's 110. This is looking great. My formula is wonderful. But did you notice what I had to do there? In question number 4, I had to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I had to count the number of terms, because I saw that 20, but I remembered, oh crap, that was counting by 2's. I didn't really have 20 terms. I had 10 terms. And 10 terms divided by 2 is what gave me the 5 pairs. So I'm getting a bit ahead of myself. I thought my formula was great, but it turns out just knowing the number of terms isn't as easy as just looking at the last number. The last number is only the number of terms in the series if you're counting by ones. Number 3 had 50 terms in it because I was counting by 1. But number 4 doesn't have 20 terms in it. You were counting by 2's. So now we have another quandary. Here I have a formula that, again, isn't quite as helpful as I thought it would be. Now we have a powerful moment for some reflection. How can we make our formula better? Again, if you're wondering why I keep looking for a better formula, why am I not happy with the formula that we have, it's for questions like number 5, letter C. Do I know how many terms are in that series? Do I know that if I start at 15 and end at 205, that I'm going to plug in a specific number for total number of terms? So I'll be honest with you, right now, I don't know. I mean, I can count 15, 25, 35, 45, 55. I can start counting on my hand until I get to 205, and I can figure out how many terms are going to be in that series. But ooh, remember that idea that a formula is supposed to make the tedious stuff better? I don't know that that makes this better at all. This still seems like a really difficult problem. 7-year-old Gauss was probably not sitting there counting on his hand for minutes and minutes. So how could we think like Gauss? This is where I'm going to end this video, because I want to end on a bit of a cliffhanger. And between now and the time you start the next video, I want you to try to channel your inner Gauss and think, how can we adapt? How can we take our formula, which was looking so promising, it was looking so good, and how can we make it even better? How can we know how many terms we have without just looking at the last number? We know it's not going to work. This series doesn't have 205 terms. We know that. It's counting by tens. It's skipping a bunch of things. We know that it's not going to work. So channel your inner Gauss. How can you predict how many terms letter C is going to have? And how can you generalize your formula to make a problem like letter C work? Take some time to think on that. And again, if you come up short, if you're really not sure what to do, then the next video will explain. But try to take this opportunity on your own to think for yourself a little bit. Channel your inner Gauss. See what you come up with.